Hello, my name is Vina Lakani. I'm a scientist one at DILIsym Services, a division of Simulations Plus. This poster presents a project that was brought to us by a client asking us to investigate their compound, which we've blinded here as compound V, um, and to assess whether their compound is responsible for drug-induced liver injury. And furthermore, what was motivating it was this compound was given in phase 1 clinical trials to a handful of volunteer patients, and a few of them developed ALT elevations. And so our task, they came to us with the questions of, was it their compound that was responsible for those ALT elevations, which indicate hepatocyte cell death, and worst case might lead to drug-induced liver injury. And if their compound was the primary driver for that cell death and those ALT elevations observed, what mechanisms might their compound be triggering, and to what extent does the compound concentration play a role in the liver? And so typically what we do with DILIsym is we take two big pieces of information to make those predictions. DILIsym is our flagship software that is considered a quantitative systems toxicology model of drug-induced liver injury. And DILIsym really investigates three of the major mechanisms for causing hepatocyte cell death. The first is bile acid transporter inhibition. Second is mitochondrial dysfunction, which we'll get into a little bit, and the production of reactive oxygen species, or oxidative stress for short. And so to get information on whether that molecule is causing or triggering any of those mechanisms, we typically outsource the assessment of that, of vitro assay assessment, to third parties. The first being bile acid transport inhibition. So for example, we would contact Solvo, who we work with very closely for this assay, and ask this proprietary compound, does it inhibit any of the four major bile acid transporters that are associated with drug-induced liver injury, or DILI? And those four are listed here: NTCP, VSEP, MRPs 3 and 4. And so typically what we can do from that assay is receive or parameterize any sort of signal there, signal being this compound does inhibit activity of one of those, or all of those transporters. And that signal will be translated into an IC50 value, for example, if there is such a signal. A second, two assays that assess mitochondrial dysfunction or the capability of the compound to produce oxidative stress is contracted out to Cyprotex. So mitochondrial dysfunction uses the Seahorse XF analyzer, which spits out oxygen consumption rate of HepG2 cells when exposed to this compound. So for example, with this compound, it was found that higher and higher concentrations of the compound lead to lower and lower oxygen consumption rates in HepG2 cells. And what we do with that sort of dose response observation, or in vitro observation or measurements, is to parameterize it and as an electron transport chain inhibitor. What this means is the compound is inhibiting the activity of proteins in the electron transport chain, like complex 1 or 2 or 3, and therefore reducing the oxygen consumption that the mitochondria consume, and therefore reduces the ATP output of mitochondria. And of course, with decreasing ATP, it can lead to apoptosis, or even just in general hepatocyte cell death. And then thirdly, Cyprotex also uses high contrast screen assay to evaluate whether the compound produces any of these reactive oxygen species or just oxidative stress in general. And in fact, this compound also was shown to have production of these oxidative species. And so unfortunately, this compound did have the potential for causing hepatotoxicity via all three mechanisms. And that's one big piece of information, is the capability of the molecule to cause cell death and which mechanisms by which that happens. The second big piece of information DILIsym requires is the exposure then of the compound in the liver, to the liver. So now we know, to evaluate that, we go to our sister division's flagship software, GastroPlus, to build a physiologically based pharmacokinetic, or PBPK model, to estimate the liver concentration of our compound. And so what we did is we took single dose clinical data, plasma exposure specifically, and built a model around those clinical observations. So we adjusted liver KP values, some values that are specific to the compound. A lot of them are predicted within GastroPlus using ADMET Predictor. And so a lot of these parameters were kind of fine-tuned until we got a simulation result from GastroPlus that matched the single dose observations that the client provided. So once the model was sort of built and trained on single dose data, we then turned to the multiple dose data they provided as a validation. So there were two different sets of multiple dosing regimens. So the top one here shows 1x dose given every day, and the bottom panel B here shows a 4x higher dose given every 3 days. And so sort of the three different subpanels here are just showing three different time points that were measured clinically. So the thick black lines are clinical data of plasma exposure. So for example, on day 0 through end of day 1, sort of this is the exposure that we've seen in the thick black lines. This is data from day 14 and day 28 through 29. And then the bottom panel, because this was given every 3 days, they took measurements from day 0 through 3, through 15 through 18. They asked the patients back finally from days 27 through 29. So those are the thick black lines, are clinical data. And then underneath those are these thin red lines that are taken from hot PBPK simulations within GastroPlus. So these are 285 individuals that we simulated by varying some of those parameters that I discussed earlier. A lot of those parameters are built into GastroPlus already. Small variations in duodenum length, more importantly, like liver KP values, and other ways, and just sort of liver clearance values and so on. And these small variations in parameters produced variations in the exposure of the compound to the liver or to the plasma in general. And so what we're showing here is that the model was built on single dose data, which is not shown, and it was sort of validated using multiple dose data, which we are showing here. So you can see that the pop PBPK simulations in thin red very closely agree with the observed clinical data for the multiple dose study. So now we have, so that completes the two big pieces of information we need to move forward with DILIsym, right? So the first one was, how much does this compound cause hepatocyte cell death or hepatocyte death, with the three different mechanisms we discussed? And second, how much of the compound actually gets to the liver to then, to be able to cause that cell death through those mechanisms? And again, that second part was determined with a PBPK model developed in GastroPlus. So when we ran those simulations, DILIsym sort of integrates those two big pieces of information. DILIsym did show that this compound has the ability to produce ALT elevations, similar to the ones that were observed clinically. As we mentioned earlier, unfortunately, this compound does trigger all three mechanisms of hepatotoxicity. So one exciting thing you can do with in silico modeling, and specifically DILIsym, is to turn each one of those mechanisms off or on systematically, and we can then determine and pin down exactly which mechanism or mechanisms, plural, are responsible for this compound causing toxicity or cell death. So, for example, this top, so we ran the full SimPops 285 individuals to show those signals in general, and then we pick a subset of around 15 individuals that had ALT elevations above 3 times the upper limit of normal to do this mechanistic analysis. So that's what this top row shows. When all the mechanisms are turned on, we have 15 individuals that have ALT elevations. The second row shows the ROS mechanism being turned off. So that's the compound is no longer simulated to be producing oxidative stress, but is still causing inhibition of the electron transport chain. and inhibition of bile acid transporters. In that scenario, you no longer get any of those 50 individuals with ALT elevations. And we sort of repeat that with turning the ETC, or electron transport chain inhibition, off, and then separately the bile acid inhibition off. So these top three, and sorry, to complete that thought, the last two scenarios there show no change at all in the number of individuals with ALT elevation. So these sort of top three results show that the ROS mechanism is necessary for producing those ALT elevations. If you have it turned off, it does not produce any ALT elevations. If it's turned on, then it needs to be turned on in order to produce any of those. Sorry, I think this first statement applies to as a conclusion for the top three. The bottom three here show two mechanisms turned off and only one mechanism evaluated at a time. So here's where we get that second piece of information I jumped ahead with a second ago. When you have the ROS mechanism turned on by itself, so no other mechanism is turned on, you still get all 15 individuals with ALT elevations. And if ETC inhibition or bile acid are the only ones turned on, then there's no response. And so in totality, you can take your time and look at this table, but it really shows a very fantastic result here that this compound produces cell death, hepatotoxicity or cell death, through the reactive oxygen stress production of oxidative stress through that mechanism. And that mechanism is both necessary and sufficient for producing that cell death. So this is one really exciting result we can get using DILIsym and in silico modeling in general. The next piece of information kind of goes back a bit of a step back to when we developed this PK model. We noticed that one of the more important parameters for developing that model to determine the exposure of the compound was the liver KP value. And so typically we like to have a really good measure or estimate of this value to move forward. But unfortunately, this client did not have, for example, QWBA studies in rats that would give a really good estimate for the value. So we tried two different approaches. One is the very simple and straightforward in silico prediction. And so we turned to ADMET Predictor, again, also available within Simulations Plus. Based strictly on the structure of the compound, it was able to predict a KP value of around 3.3. And separate data point to estimate the value, we turned to the in vitro assays that we had contracted out. And in those in vitro assays, we measured the intracellular concentration of the compound and the supernatant. And so we can take a ratio of those two values, and the in vitro assay then estimated a value of 0.33. So there's a tenfold range, a whole order of magnitude that we sort of had, but to work with the liver KP value. So the in vitro estimate was around 0.3, but the in silico estimate was around 3. So one thing we can do is to run the simulation with both of those values. And if you use the in vitro estimate, DILIsym predicts absolutely no one out of the entire 285 individual SimPops, 285 SimPops, has ALT elevations. On the other hand, if you use the in silico prediction, there is an incredibly high percentage of the individuals simulated that had ALT elevations, at least 62% or 61% with 1x dosing, or almost 90%, over 90% of the Q3 dosing. Both of these are outside the range of what was measured clinically. And so we estimated a few more values. So we interpolated that. Sorry, not interpolated. We took a few values in between those two extremes and found that the liver KP value of around 2.1 produces a percentage of ALT elevations, simulated percentage of ALT elevations that were most similar to what was observed clinically. So in short, what we were able to do with DILIsym modeling here is, because they did not have an estimate for the liver KP value, we're able to sort of estimate the value for them using DILIsym modeling, and to show that the value might be around a value of 2. Still, we encourage them to move forward, and one of the maybe the better next steps for them to take was to do a preclinical study with rats and estimate the QWBA study to estimate the liver KP value. The other complicating, we have a few more conclusions here, and sort of related to that is that this compound is highly lipophilic, and its target patient population is patients with obesity. So with obese patients, there's a high amount of liver fat, or there can be a high amount of liver fat in obese patients. And so, in fact, the liver KP value might vary because of that, right? This compound is lipophilic, and there's a highly variable amount of liver fat in the patients, then that might very significantly affect the liver KP value, which then in turn affects the exposure to the liver of this to this compound, and therefore the toxicity potential toxicity because of that. So the second suggestion we made was to maybe estimate whether there are implications of the liver KP value due to sort of the content, liver fat content. And this can be done in preclinical species. So I think it's a good place to stop here, and I can sort of run through the conclusions one last time. I think one of my favorite parts of this project was to see that DILIsym can be used here to really pin down which mechanism is responsible. Because this compound, if you just looked at the in vitro assays and sort of contracted them out, you just looked at them by themselves, you would think, oh my gosh, this compound is triggering all three of the mechanisms. It could be anything. But in fact, with DILIsym, we're able to pin down, actually, it's specifically this oxidative stress production that is necessary and sufficient for this molecule to cause the observed ALT elevations. So that's a really exciting thing. It sort of encourages the client to say, we know we have signals in mitochondrial dysfunction, that's the CTC inhibition, and potential bile acid inhibition, but those two mechanisms are not as critical or as likely to be causing this ALT elevation as this oxidative stress. Yeah, so I'll stop here. And unfortunately, I cannot take questions, but please email me if you would like to. My email address is here on the top left. I'm expecting a baby very soon, and so I am out for the next few weeks. You may please reach out also to anyone at DILIsym at Simulations Plus for more information on DILIsym software, GastroPlus software, Admit Predictor, I think I've mentioned in this project. So thank you very much for your time. Please feel free to email me again.